Hey guys, welcome back to another video. This video is going over additional problems with resonance structures. So if you want an overview on resonance and kind of a step-by-step guide of the common patterns in resonance, delocalize and localize lone pairs, you can check out the video prior to this one. This one is just going over a few practice problems that I have here. So you could see these practice problems on your homework, on an exam, quiz. These are pretty common problems. So let's get started. This one asks to draw the significant resonance structures for this following compound. So let's use this compound as our first resonance structure. Again, this is resonance structure number one. Even though we didn't change anything, this shows up in nature with the other structures that we're about to check out. So let's make our double-headed arrow and see what we can do. First thing that you guys should see is that we have this going on right here. We have a pi bond with a carbon and an oxygen. That oxygen is far more electronegative than that carbon is. So we can do resonance right there, and let's do that. Let's pull out one of those pi bonds and make a second resonance structure. Now that oxygen has only one bond and that carbon has three bonds, so it's going to have a plus and a minus. All our other pi bonds stay the same here. And now the next thing it should signal is that we do have a ring. It's not a benzene. There's a couple more carbons to make it a benzene. So it's not a benzene, so you can't resonate all the way around the ring, but you can resonate somewhat around the ring. So we can take this pi bond right here and resonate it. Resonate that plus carbon charge inside the ring. So let's do that. So we have a double bond up there. Oxygen stays the same as a negative charge, and our two bonds down here stay the same. So where will this plus charge end up? Well, it doesn't end up right here because that carbon has its four bonds, but this carbon right here only has three bonds. It started with three bonds. We have a double bond and a single bond and one hydrogen, and now it only has 1, 2, 3 bonds with that hydrogen. So it likes to have 4, it only has 3, so you give a plus 1 formal charge. And now we can incorporate this pi bond and resonate more around this aromatic ring. That pi bond goes up there. Everything up here stays the same. And our plus charge goes right here. And finally, we can do it one more time. Put that pi bond over 1. And we'll have our final resonance structure. With the plus charge going over here. And that is your final one, because this pi bond can't travel all the way over there. There's too many bonds in between that wouldn't be observed. So this would be your final resonance structures. We have 1, 2, 3, 4, 5 resonance structures for this problem. So really pay attention to those common patterns. There's 5 common patterns for resonance. I told you guys in that previous video, if you do enough resonance problems, they start to come naturally. So let's keep going. Right here we have 3 different problems. It says to draw all significant resonance structures for each of the following. So let's start with A. Let's just rewrite this. Okay. And let me fill in the lone pair for that nitrogen and this oxygen as well. All right, so there's a couple different things we can do. We have a nitrogen that has it's filled octet. It has 3 bonds, and it also has that lone pair. And that's one of the common patterns that we see with resonance, is that if you have a C plus, a carbon plus, next to a lone pair, it can resonate with that. So let's do that. Now the nitrogen is going to have a plus. And that is one resonance structure you could do. All right. Now there's one more we could have done here. We also have lone pairs with this alcohol group on top. So I'll show that in this next one. Let's say this pi bond goes back to its original place. That's not a good depiction. Let's see. Let's make another. How should I do this? Let's say these pi bonds go down and these go back to this nitrogen. Okay, so that lone pair comes back, this oxygen drops down, and that oxygen now has a plus charge. So I was thinking about in my head if I should rewrite this again, and then instead of showing two arrows, I would only have to show one, but this serves its purpose too. This shows that the pi bond is going back to its lone pairs on the nitrogen, and the lone pairs on the oxygen comes down to make a pi bond, which leaves a plus charge on that oxygen because it now has 3 bonds when it only wants 2. So that's the first one. Feel free to pause it. For the sake of room, I'm just gonna erase it, and let's go on to question B. Start with our first resonance structure. Okay. Now, first things first, C plus next to a pi bond. This is our pi bond. This is our C plus, so we can definitely resonate with that. And our plus ends up right there. And then you have, let's see, lone pairs that I didn't show. On that oxygen, those lone pairs can be pulled in to make another pi bond, which would be our final resonance structure. And you should end up with a +1 formal charge for each of these structures. All right, pretty straightforward. Recognizing the pi bonds, how to move them. Remember that when you always start with a formal charge of +1, that has to stay +1 through all your resonance structures. If you start out with resonance structures that have a formal charge of 0, then everything has to be 0. You can have a plus and minus that equals 0. Let's say you have a +1 formal charge on an oxygen, and you have a -1 on maybe a C minus, a carbon minus. Those can still equal 0. So all your resonance structures should stay the same formal charge throughout. All right, let's go to question C. Again, same principles. We have our C plus next to our pi bond, so we can move that pi bond over, and let's do that. Where does our C plus end up? Well, originally this one had 1 hydrogen, and it still retains that 1 hydrogen, so this has 4 bonds. But this carbon right here used to have 3 bonds and 1 hydrogen. Now it only has it had 4 bonds, no hydrogens, because there's 1, 2, 3, 4 bonds, and now it only has, let's erase all this, now it only has 1, 2, 3 bonds. So your plus charge is going right there. Okay. Going on in resonance, we can make another one where we drag this pi bond over. Oops, too many carbons. And your plus charge goes over there, and we can make a final one by dragging our last double bond over. All right. And all of our structures have a +1 formal charge on one of our carbons, so that all checks out. All right. So this is your next problem. We have our first resonance structure here. This asks to draw all the resonance structures for each of the following compounds. So let me redraw this first one. And I believe these are shorter problems, so you should only end up with 1 or 2 structures here. So the first thing we can do is recognize that this formal charge is equal to 0. So any structures that we make should have a formal charge equaling 0. So we should have a plus or minus when we end up with resonance. So let's see what we can do. The first thing I would do is fill in these lone pairs, and let's see what we can do. So we have a pi bond. Let's see what happens if we put that pi bond over on that oxygen. Let's see what happens. We would have a plus charge right here because this used to have 4 bonds and now it only has 3. And this has 2 bonds. That oxygen used to have 2 bonds, now it has 3. So we end up with a plus and plus. Now that isn't really shown, right? Because we should have resonance structures that equal a formal charge of 0. So this is incorrect. We have to think of something else we can do. Okay. Now let's think about pulling that pi bond into a lone pair. Instead of pulling it somewhere else, let's put that pi bond, let me use red. Let's put it in a lone pair. So what I mean by that is it ends up looking something like this, where you have a lone pair right there and a negative. And then we can put these lone pairs of this oxygen into a pi bond. So this will end up with a plus charge on the oxygen and a negative charge on our carbon. All right, so that's the first problem. It took some engineering to kind of think about what we need in those formal charges. Let's go on to part B. We have 2 lone pairs on this oxygen. It has his octet filled, but this carbon does not. So let's think about what we can do to fill that carbon's octet. We can pull one of these lone pairs off to get that carbon its 4 bonds. So this carbon is now good. That carbon's neutral, but now our oxygen has a +1 formal charge because it has 3 bonds now. So only 2 resonance structures you can do for A and B. Now take a picture if you want to check these out. I'm going to erase them to go through C and D. Hopefully resonance structures are getting a little bit easier for you guys. This one we have an unfilled octet for one of our carbons, and we have a pi bond right next to it. So we can pull that pi bond out from its double bond. And where should that plus end up? Well, let's think about this. This carbon has 4 bonds. This carbon has 2 bonds right here and 2 hydrogens. And when you pull that pi bond away, this carbon has 2 hydrogens still, but it only has 1 bond. So now it has 3 bonds. So that's where your plus charge ends up, at this carbon. All right, and that's the only resonance structure you can do for this one. Part D. We have this nitrogen with 1 lone pair. It is neutral, so whatever we do, we want to make it neutral. So we want our formal charge to equal 0. So one thing we could do, let's test out a few different things we can do. We can pull this double bond either onto the nitrogen or onto this carbon. Let's see what happens when we pull it onto this carbon. That gives you a negative charge. And this nitrogen only has 2 bonds. So that gives a negative charge as well. So that does not work. We have a formal charge equaling -2, and we want a formal charge of 0. So we need to do it the other way and see what that gives us. So again, resonance structures are a bunch of trial and error. Let's see what we do when we put that double bond onto that nitrogen to give it second lone pair. Now that nitrogen again has a negative charge, and our carbon now has a positive charge because it doesn't have any lone pairs, so it needs another bond. It only has 3 bonds now, so that why it gives a +1 formal charge. So that is your resonance structure for that one. All right. So this question asks, which of these structures exhibits an sp3 hybridized nitrogen atom? Now there's a couple ways you can think about this. You can think about what is different with all these nitrogens. So ask yourself, looking at all of these, where do the pi bonds end up on the nitrogen? So for this one, we have no pi bonds. For this one, we have pi bonds that are away from the nitrogen. This one, we have a pi bond that's away from the nitrogen. But this one, the double bond is right next to the nitrogen. And again, this is a multiple choice problem. So you have to think about, how does this make sense? Which one is different? I would say C is your sp3 nitrogen. Now you can get into aromaticity if you go into organic chemistry too, and this can help you explain if something is aromatic or non-aromatic. But if a double bond, a pi bond, is directly connected to your oxygen or nitrogen, that makes it sp3. If it's not directly connected, like it is for A, B, and D, then you're dealing with an sp2 hybridized atom. Okay. This question asks, which of the following anions is resonance delocalized? So what does delocalized mean? You guys can check your notes, but delocalized means that it can resonate. All right. So what does that mean? Which one of these can resonate? So we have this one right here, we have this one right here, and we have these lone pairs. Always fill in your lone pairs if you're unsure. And again, this is a multiple choice question, so we can think about these one by one. So let's think about this first one. Let's think about 1. This can resonate, right? If you pull that pi bond up, you get a negative carbon at the end there, and you get a fully octetted, I guess is a word, that oxygen has a full octet. So you can definitely do resonance for this first one. So all of these, B and C, are knocked out. So we don't even really have to look at number 2, we just have to look at number 3, process of elimination. So is number 3 delocalized? Is the following anion resonance delocalized? Well, we can do one resonance structure, but is it correct? So we can pull one of these lone pairs out from under there. Our oxygen now has its full octet, but we did something we don't really like to do, and we have a carbon with 4 bonds, and now that carbon has 5 bonds. We're breaking one of those commandments that I shared in last video, where you really don't want to overfill or exceed your octets. So this wouldn't be a proper resonance structure. So actually, the correct answer is A. 1 is our only delocalized anion, our only delocalized oxygen there. So again, ask yourself, can these structures resonate? That will lead you to the correct answer. And that is all the problems I have for you guys. Hopefully you found this video helpful in doing resident structures. It's a bunch of trial and error. If you go through enough resident structures, you'll get really good at it. So I will see you guys in the next one.